Welcome to the first session, the workshop on effective metabolomics software from design to practice. We'll have 4 speakers in the session. I'll be starting off the presentation. And after me, we've got Jenna from Metabolomics, Atsushi from Riken, and Jeff from, Jeff's actually moved to University of British Columbia. My apologies for the mistake there. So each of us will be covering different aspects of what we want to talk about in this workshop as we go along. And the bigger picture goal that we have in mind at the end of this workshop, what we want to achieve is basically to enhance efficient software design and development in metabolomics bioinformatics softwares. So fundamentally, by going through all the basic principles and the different technologies, different software practices, what we want to achieve at the end of the day is software engineers and programmers who are here to go away and start thinking about imposing all these very important concepts in the softwares that you've built in metabolomics. And that way we get good quality software that lasts for a long time, that is more reliable, and that's more scalable. And from my perspective, now I'm going to make a case, and I would walk through it towards the end of my talk. I'm going to make a case to the metabolomics community to move towards more of a collaborative software development methodology as opposed to the other models that we've been working on primarily. Now, the reason we're talking about softwares here and the reason we've got sessions like this is because we as a community do realize the importance of softwares in metabolomics as a science. And we know that softwares are an intertwined part of metabolomics. As you can see, we've got softwares contributing to every part of the metabolomics workflow, starting from your raw data collection all the way through data processing, statistical analysis, visualization, and data interpretation. And you've got some of the well-known examples there on the side there. And these are softwares that take part in your regular metabolomics workflow. And on top of this, you've got several large-scale software systems that contribute to other aspects of metabolomics. You've got large LIMS solution, laboratory information management solutions, MasterMS, the system that we developed at Metabolomics Australia, and you've got NIH Metabolomics Workbench, and large data repositories such as Metabolites, Metabolites, and database systems such as MassBank. Now, these are systems that work on a much higher level than your regular workflow. But bottom line, the take-home message from this slide is that we've got software taking part in almost every component of metabolomics as a science. And now that we realize, and now that we've always known really, that that softwares are such an intertwined part of metabolomics, the argument that we're going to make through this workshop is that care needs to be taken about how we write these softwares and how we develop these softwares. At least as a fundamental thing, we need at least these 4 properties for every software to uphold. Software needs to be reliable, it needs to be reproducible, scalable, and easy to use. Now, these are just 4 very generic concepts, and of course, when we start talking about more seriously, we'll have several other important factors that a software needs to possess for it to be successful. And by reliable, we're talking about a software that is error-free. Of course, it's impossible for you to have a software that's completely error-free. Reproducibility, we need softwares that are able to reproduce the results every time for the same data set that it takes in. And this is not necessarily the case for really, really large-scale systems that's got several thousand modules and communication happening across every module. And we need systems to be scalable. So when I write a piece of software, someone else wants to take on that software, build on top of it, they should be able to do so with ease without having to modify too much of my content, and someone else should be able to build on top of that with ease and basically make it bigger, better, stronger, and basically more useful. And of course, systems needs to be easy to use. We are very well aware of systems that are technically excellent, but just do not have the ease of use in mind when it was built, and hence they just lay idle. So bottom line is that when important factors like these are not taken into considerations, softwares fail. And when softwares fail, you could have drastic consequences. Now, of course, these are drastic examples, but true nonetheless. Just some of the examples in 1987, the software failure caused the death of 3 people. 1999, the well-known loss of Mars climate orbiter because of a software bug. And more recently, in 2006, a group from Scripps had to retract 5 high-impact papers because of a bug in the software that they inherited from a different group. And those are just examples of reliability. And of course, you've got issues with reproducibility. And as I already said, now this happens with extremely large systems with thousands of moving parts and interactions happening everywhere. And the authors of this paper determined that not all computational softwares are really reproducible. It's quite difficult. And as already we've mentioned, we've got too many examples to point here about softwares that have issues with scalability and ease of use. Now, these were general observations for computational softwares, but metabolomics softwares being scientific softwares, all these problems would be eventually present in the softwares that we have in our community as well. So now that we've identified the problems behind softwares and what could happen, we've got to start thinking about why these softwares fail and what are the primary reasons behind what we see. And one of the first things that happens is because of the complex nature of the software itself, because you've got so many modules and you've got so many moving parts, and you're bound to have errors in it, bugs creep into the system, and we can't do anything about it. But the more important reasons of why softwares fail is because of the next 2 points that I've mentioned here. It comes down to who writes the code and basically how they write the code. So in today's bioinformatics scenery, we've got 2 types of researchers writing code. One is researchers who are basically trained as biologists, and they've moved into computer science, they've learned programming, and they write code. Now, on the other hand, you've got researchers who are trained as computer scientists or programmers, and they've moved into biology and hence become bioinformaticians. And finally, we've got students who are a bit of both, really. Now, the problem arises when this group here messes up, and we usually end up doing so. So where the problem arises is when either a researcher who's not formally trained in the fundamental principles of software engineering does not impose these because they're just not trained for it, or on the other hand, if you've got researchers who are trained, but they just do not have the time to write a properly fundamentally strong software because of several time factors. I mean, we know that we hardly have people who work on software engineering projects full time, especially if it's a smaller group. So you've got one person who's trying to do all, and this is when errors seep in. And this is the next most important thing. How do they write the software? And there are several models in which software is being written, and a vast majority of the cases, the heroic programming model is what is being followed. And it's an interesting name that comes from this paper back in 1995 in IEEE software. A nice paper to read. So fundamentally what that model says is that it says, and you would relate to that very well, it says that a person basically tries to do everything in software engineering. So they try to be the technical architect, they establish the systems design, the technical architecture, they gather the specifications, they write the software, they test the software, user acceptance testing, and the whole lot. The whole thing is done by a single person. And as you can see, these are different talents that are required from different people. If you move into the software engineering industry, you would have a separate person doing every bit of that piece that I just mentioned. But in the heroic programming model and in science, we've got one person trying to do everything, and naturally that opens up room for error. The other 2 models that we are not quite into in metabolomics bioinformatics is collaborative project model, where more than one group works on the actual development of a software. And extending that model is the community engagement model. We've got the entire community working on large projects. Now, the picture that we have right now is we've got researchers here who either are not trained in the fundamentals of software engineering. You've got researchers here who try to take the easy way out, working on the heroic programming model, where they try to do everything. So as you can imagine, this is an opportunity where lots of errors and issues seep into the system. So now that we've identified we've got issues, and we may have issues, and the problem with these issues is that we would not quite know until it's a bit too late, so it's better to be proactive. So the question is this the time to start thinking about? The answer is yes, absolutely. Now is when we have to start thinking about being proactive. The reason is we've all seen the exceptional growth of metabolomics as a science in the past decade and half a decade. We've got more and more groups working on it, more funding is coming through, and we've got more groups using metabolomics as an application science. Especially in service facility, we see this a lot. So the growth of metabolomics is unquestionable. So what this also means is that we'll get more money coming in, we'll get more people writing softwares and more softwares coming out. So this is probably a very good time to stand back and think about how to do it right. So, and what are the practical steps that we ought to take for this to happen is basically what we're doing right now, training sessions like these, where researchers with different experiences in this area come and basically teach us about how to do and what are the best approaches to follow. And this is a case that I am going to make, is that we as a community, metabolomics, bioinformatics community, try to move away from the heroic programming model towards more of at least a collaborative model, and eventually, hopefully, into the community development model one day. But we do have some current collaborations in the area of metabolomics bioinformatics these days, especially primarily in the data standardization area that it's led by Metabolomics, and they're doing a fantastic job in bringing different groups together to agree upon things. The case that I'm making is to move towards a more collaborative approach in actual software development itself. And this is not going to be a straightforward exercise that every software engineer here knows. It's going to be very, very difficult, but once we overcome the difficulties, I believe the benefits would far outweigh the risk and the effort that we would take. And of course, the actual details on how we are going to do this is yet to be thought about and determined. And this is even more important for large-scale projects and extremely large projects like the master MS LIMS systems that we've been creating, because the larger the softwares are, the harder they fail. Because if we can't afford to make mistakes there. So more pairs of eyes are absolutely a fantastic thing, and hence a community-based development model would be really good. And as a very first small step towards this effort, Metabolomics Australia and ABI over the past 1 year have been working on integrating ISA tab into our master MS LIMS systems, LIMS solution that we've developed, which we'll talk about later. Again, it's at a different talk. So I would like to end this talk with, as I already said, a call to the metabolomics software development and bioinformatics community to start thinking about more collaborative software development projects. I'd like to thank my group at Metabolomics Australia, the University of Melbourne. That's my group there, and we've got the group members from ABI. And I'd also like to thank my colleagues at the Australian New Zealand Metabolomics Network in the ANZ region. Thank you. Got a couple minutes for questions? Everybody's happy? No. Yeah.
So when you say software here, you're talking about sort of standalone packages that are being used by large numbers of people.
Yes. Well, both.
What you're talking about, I mean, there's a lot of programming that happens in the context of data analysis that should be reproducible, but certainly not. Most of the time, much of the time, I totally agree with you that these principles can be used for both aspects of
Well, what I had in mind is, I mean, I can understand why it may be a bit difficult to do such a thing for extremely small projects. I mean, you probably don't have interest from the other groups, but wherever it is remotely possible, I would suggest we do this. And my primary concern comes from, one or two people writing a software and then probably moving on, or and not working on it anymore. My argument is that if you have more pairs of eyes looking at it, or two different groups working on the same project, I mean, it does not even have to be co-development. Someone else keeps an eye very closely, and that would really, really be helpful in the long term, because we've seen too many examples of softwares that are just sitting idle there without being used. Yep.
So there was a recent blog article by Jonathan Eisen talking about the model for reproducible software, and his model was that researchers should, from the start of a project, have a GitHub or similar public repository, make all their code completely available. At the end of the day, they should include a virtual machine that has everything wrapped up in it so that it can be rerun maybe mix the code into things like the Galaxy programming environment that's really useful for modularization of code. Do you think that type of complete openness is essential for this type of sharing and reproducibility?
Absolutely. I think that is extremely crucial, that we make everything open and as open as possible, including the exact environment in which it was built, because that would be the best way for another group to even to keep an eye, let alone replicate the system and see what's happening there. Absolutely, I agree with you. Any other questions? Yeah, back there. What is going to... the challenge in making this happen?
Exactly, yeah.
Well, exactly. I was chatting with the other speakers here, and we do realize that it's going to be an extremely big challenge to make this happen. And I guess as a first step, in the least, what we can do is what we were discussing now, in the sense we write a software and we have another group keep an eye on it and follow it very closely, primarily to pick up any mistakes that we've done. It could be fundamental core mistakes in assumptions that we make. What would be ideal is we can have multiple groups coding together in the same. And of course, we do have community engagement models. The Linux is a fantastic example of a very successful outcome. But yes, much more thought needs to be put into it, really. Yeah. And we need to have willing partners to do that. Yeah, absolutely. Oh, sorry, I think we're running out of time on Access. I'd like to introduce the next speaker now. I'd like to introduce Jana Hastings. Jana is the group coordinator at the Cheminformatics and Metabolomics group at EBI. Jana is, her educational training is a master's in computer science, and Jana spent quite a lot of time in the industry before she moved to EBI. So I believe we've got quite a lot to learn from Jana's experience. Jana?
So this is really an honor to speak here in this wonderful symposium, in this conference. Since I joined EBI 8 years ago, nobody has ever asked me to speak about software engineering. And I love this opportunity because it's so important. But in a research environment, software engineering best practices tend to fairly often get overlooked. And that's just an unfortunate side effect of the sociological challenges of always having slightly too few people to work on any given software project and always having deadlines and other priorities. So I thought, well, what could I say about software engineering given the opportunity? And I thought, well, I'd love to talk about best practices in 10 steps even. Each of these steps I think is quite easy, but the problem is they do tend to contradict each other sometimes. So the first best practice that I would really like to recommend is, if you're tackling a software engineering project, do the simplest thing that could possibly work. It's amazing how many times people start out, wow, now I'm going to try really, really sophisticated engineering and come up with a massively elegant and sophisticated solution to this really simple problem, and they spend months doing it, and at the end of the day, something else has cropped up and they never really finish. So keep it simple, start out with simple. If you need to, you can always make it more complex later. For sure, after the first time you write your system, you will understand the problem better, and half of what you've written, you probably need to throw away if it's a living system and it keeps evolving. In the larger systems which tend to have in industry settings, it can make sense to take a really slow, measured approach, design first, then implement things in stages, do testing, and then release. And that's, the old style waterfall model of software development lifecycle. But what's much more, I think, popular these days and more relevant to a research environment is more agile types of iterative development. So start out with a small subset of your overall software requirement that you need to develop. Really, really put your hands quickly into the code, get something out there, and then revisit it in iterations. And there's a lot of information out there on agile software development that you can look up to help you. A fundamental and very important message for software developers is don't repeat yourself. It's amazing how often you get into a habit of just, oh, I need to do something, it's sort of similar to what I did before, so I'm just going to copy that old script and change 3 or 4 things, and I've got a new script, this is great, this is easy, it works. Unfortunately, when something like your database infrastructure changes, you have to change all 20 of your scripts where that database, nice little snippet of code that connects to your database has been copied and pasted. Of course, it worked, but now you have to change it 20 times. So just never do that. Every time you find yourself copying and pasting some snippet of code, write a library function. You'll be glad of it afterwards. Don't repeat yourself. So writing library functions lends itself to having a modular design for architecture. All those methods that you're going to reuse over and over in different contexts, take them out, package them up, put them into a module, give the module a name, give it an independent existence, publish a interface which is really easy to understand with nice readable method names, and then you can call it from the other modules. So modular designs are helped along by object-oriented programming languages such as Java and more modern scripting languages such as Python. You won't regret it if you design really good modules. This is a message which can't be said often enough. Start testing right from the very beginning. Keep testing. Get people to test your system other than yourself. Test your system yourself. And most importantly, write little units of software that test other bits of the system. Those are called unit tests. And the nice thing about unit tests is that you can schedule them automatically. So as soon as you've written it, you can keep running it over and over. A lot of developers run their unit tests overnight or every time they make a commit. And then it's really great to know that your system is healthy. Nothing, you think that you're not going to make any mistakes. You think that you're not going to break some other part of the system when you commit something in this totally unrelated part of the system. But you are. You won't realize it. And your unit test will pick it up if you've got it. But if you haven't got a unit test, it'll be your user who picks it up. So, write those unit tests. Very important. Find some users. In a research setting, we are often our own users. We write the software for ourselves. We don't really intend a lot of other people to see or to use the software. But increasingly, as more and more software gets exchanged in libraries, and I think giving the background to this workshop, it's because that's happening. People don't have the time to rewrite over and over the same software functionality, so they need to use shared libraries. And so then you have users, and find them and ask them to beta test. Get them involved if you can. If you can do it open source, that's great, because then you can get your users to become co-developers. They can help you squash bugs. They can help you extend the functionality in ways that are useful to them, but you didn't have the time or the funding to do. If you're working in a closed source model, then it's a little bit harder to get your users to really help you develop, but you can still involve them. Run workshops, get them, really, really looking at the software, and they will help you. Of course, the downside of asking your users what they need is that they're bound to always have a nearly infinite list of things that they need, or think they need. So it can become quite difficult if you do get all your users to give you suggestions to then limit the scope of what you're actually doing to something reasonable. And as long as I've been working in software-related fields, I must say I've never met a developer who could accurately estimate how long it takes to do something. I can't. So think, how much are you actually going to have time to do? Halve that, and then, you'll still be wrong, but you might be a bit closer to reality. So beware of those wonderful functions that seem like they'll be just so cool, but you're never going to be able to develop them. You'll end up writing the software forever, and then you'll run out of funding and it won't be delivered. Document everything. You think that you're going to remember in 2 weeks' time, in a month's time, in a year's time, when you need to go back to software you wrote yourself, but you won't remember. You'll look at the code and you'll think, what on earth is going on here? And even more so if you leave because you've got your PhD now and you've gone to another lab and some other PhD student is left trying to pick up your software and make it do additional things. They're not going to know what's going on. You really have to take the time to write documentation. So put comments into the code and then keep those comments up to date. The number of times I've seen comments that say one thing when the code was actually doing another thing, that's also really common. And write not only comments, but also really, take the time to write little guides, little booklets describing this is what this library does, this is the easy, this is where you start, this is how you get it to run, this is what else it needs. Take the time to write that and 1 million additional people will be happy to use your library. If there's no documentation, people won't use your library unless they're forced to. It's all very well to say, now you put things into modules and that's great, but modules can be written in such a way that they still have spaghetti in dependencies. And that's a real challenge in modular software engineering. So I don't know if any of you remember the days when you used to have this nice little word called goto, which you could use to get around in your code. And then you would sort of be doing one thing and then the code would say go to line 356 and start working over there. And then in line 358, it would say go to line 1007 and so on. And by the end of it, you just had no idea where you were in the code. I've seen module dependencies that work a lot like that. So make sure that your modules that you write are clean of dependencies on other modules in unexpected places. And the test for this is if you have an error or a bug and you're debugging, so you're sitting with your, stepping through in your software development environment, if you're jumping from module to module while you're debugging, something's wrong. Clean it up. Design is not good. Optimization is a wonderful thing. Performance enhancement and so on and so on. Never do it first. Always get the functionality right first. See what your software is doing, make sure your tests are in place, make sure it's working, and then start your optimization. Software that's optimized first tends to end up completely unusable in a way. It becomes very complex, and it can happen that the bit that gets optimized is actually hardly used, and something else that wasn't optimized is more often used and is more difficult to use as a result of the optimization. So always get the functionality right first. And I put a little plug in there for version control. I think version control is really, really, really important, and if you're not using version control, you're going to have a much harder time of doing anything in software engineering. So this last point, I think, is quite important, but I know that there'll be lots of people in the audience who will completely disagree. But we've seen in our group and in a lot of other groups that sometimes when you try to start over, you think it's so necessary. It's just the existing system is so awful. It's been written by 350 different people. None of them had any training in software engineering. It's full of bugs. It's difficult to maintain. And that, yes, that happens really often. But then you think, great, I'll just start from scratch. And what do? You work on it for a year and a half. You don't finish. And then you run out of time. And the existing system is still limping along, doing its thing. So think very carefully before you start again. It's really tempting. I think it's more tempting to people who actually have to sit and try and solve the issues that arise when you get bugs. That would be the actual software engineers on the ground working in the front gate. But it's quite common not to finish rewriting projects. So bear that in mind. Evolution, not revolution. So those are my 10 points, and you might have noticed that some of them contradict each other, and it's difficult, really difficult, I think, when you're actually on the ground to know what's best to do. And that's where you have to sort of develop a little bit of gut instinct and just the ability to say, hey, we tried that, it didn't work, let's move on. I think there are particular social challenges, and that might be a little bit about what this workshop is for. One of the social challenges is that the incentives in a scientific research environment do not promote good software engineering, because good software engineering takes extra time, and it's time we all don't have. So that's something to think about, and maybe the answer is to use workshops such as this to slowly bring software engineering into the scientific culture for the benefit of all of us. Thank you.
Thank you, Gina, for that wonderful talk. Questions? Got a couple of minutes? Yeah. Yes, from back there.
Your last point, you said it was controversial. You don't have to do one or the other. You can sometimes go in between. You have a large, complex framework, and you can rewrite parts of it, and not all of it. So you don't have to choose between evolution and revolution. You can choose small revolutions.
Absolutely, and I think that might even be the best way forward in most cases.
Thank you, Jenna. Right, next I'd like to introduce Atsushi Fukushima from Riken here in Japan. Atsushi is the author of Metric and their internal database called Miko. Atsushi's been working with R and bioconductor a lot, and he's been working on databases as well. And Atsushi is going to talk about database technologies. Thank you.
Thank you. First of all, I would like to thank the organizers for the opportunity to talk today. Good morning, everyone. Today I will talk about my experience of omics data analysis. So next I would like to share with you important points from software users and developers' point of view. Over the past decades, I involved in omics data analysis, including metabolomics and transcriptomics. I have divided my presentation into three parts. First, I would like to explain briefly the background. And next, I will talk about our political issues and solutions. So finally, I will make a summary. As you know, there are many big data in the world. By definition, big data means challenges our ability to move, store, manage, retrieve, and analyze information to maximize knowledge generation. So I think that one of the goals of our tasks is to explore data mining, data science, high-performance computing, database, and software development. In this context, Metabolomics community has been paid attention to this. This figure shows major processes generating metabolomic data, including sample preparation, data acquisition, and data preprocessing to generate data matrix like this. Today, I would focus on so-called downstream data analysis, including statistical data analysis, data interpretation, and hypothesis generation. So typically, we can know incomplete information about data analysis, including database and the software version. As you know, publishing a paper is so time-consuming process. It also needs data leak analysis and data leak evaluation and rewriting a manuscript. So in that case, we have to check original and processed data and our notebook again and again. I think that what we should do is to improve reproducibility and transparency in our data analysis. Here, I would suggest that you should use R and bioconductor. Typically, we describe in the R script as a log in name and date, dataset used, software version, used package name, used file name of data matrices, and the phenodata. Phenodata means metadata describing samples in the experiment. And also, directory and or folder organization is important. Using these information, we can specify the dataset used or software version later. As a practical issue, we faced a task integrating multiple data from different platforms. This figure shows the workflow. We obtained 3 datasets from GC, LC, and CMS for tomato fruit. We needed combining these datasets to generate single consensus data matrix from these multiple datasets. We achieved this by performing combining dataset by using automated data format and chemical identifier unification. And then we concatenate and summarized data of the same metabolite by using a MetaMask package. As you can see, example of summarized data matrix. So highly correlated metabolites across the sample or across the data set are replaced by principal component, the first principal component. On the other hand, weakly correlated metabolites are not replaced in the same manner. It is identical to so-called eigen gene or eigen metabolite. So this means that we extract a major pattern in the groups. To this end, we developed our R package called metric. So metric package is for downstream analysis. This package provides the function involved in data import and export, concatenation and summarization of multiple datasets, data scaling methods, and batch normalization. You can see we implemented some lead function for multiple data set. For example, LC, C, GCMS. These functions generate bioconductors expression set class. This class is a container for multiple source of information. And this is the input or output of, from many bioconductors package functions. I think phenodata is also important. So phenodata is metadata. Typically, we describe the sample of, sample ID and experimental factors, including genotype and treatment. So for data sharing, I suggest that you should document and specify experimental factors in text or CSV format. And also, you can reuse this phenodata when depositing your data with public database, Metabolome databases, like Metabolites and Metabolome Express. Next, I will present our final example. Recently, we created Metabolome database, which is called MEKO. This database contains GCMS-based metabolite profiles of 50 Arabidopsis mutants. These data are freely available in the website. This figure shows screenshots of MEKO. You can browse mutant information, including gene and gene description, and our observation under our conditions. You can see image of mutants like this. You can also check the data quality and changes in metabolite levels. MEKO has an interactive analytic tools, yes, like heat map. This is based on only R and Shiny package. So Shiny package is for building beautiful, interactive, and powerful web application with minimal effort. So it's my last message. Let's use R. Let's log your data analysis, and let's create your good experience as a package. Thank you.
Thank you, Tsushi. Questions? What, 2 to 3 minutes? No? Okay, thank you, Tsushi.
Thank you.
Okay, next I'd like to welcome Jeff Jia to talk about web technologies. Jeff is the author of the well-known Metabol Analyst software, and Jeff's background is a bit atypical. Jeff was actually trained as a medical doctor, and then he moved into everything else now. So it'll be interesting to know from Jeff.
Okay, thank you for the introduction, and hello everyone. And it is my great pleasure to be here and talk about developing softwares. As Jenna mentioned before, it's really quite rare for us to stand in front and talking about best practice to developing tools. So the task I'm asked to do is to do a review on web application development. So today I'm going to introduce some of the technologies used for web application development, and also my personal experience, how to make it better, more effective. So this is outline. First, I'm going to do a review on bioinformatics applications. And then I'm going to discuss about the server-side technologies and client-side technologies and how it contributes to a web application. And finally, it's my own perspective on the future next cool web application, what it should look like, what's technology enable us to do that. So as you already seen a similar message before, there are 4 major tasks for biological bioinformatics tools. One is data processing, and the other one is statistical analysis. Then another one is data visualization and data integration. This can represent 4 major tasks we, as doing bioinformatics, facing. So different tools usually have different kind of forms of tools to tackle it. So usually there are 3 forms of tools. One is command line tools like bioconduct package such as XCMS, which is totally command line driven. And the other one is standalone graphical interface tools, MZMine. So the third one is web application, which I'm going to discuss today. So as you can see, if you use command line tools, you have a huge amount of flexibility. If you know the code, it's basically open source. You can basically do whatever you want. But the difficult part is you have to learn the language and comfortable with the tools, the language. With it's going down from standalone to web application. Everybody is familiar with how to use a web page and click buttons and move around. So it's much easier to use. But there's kind of challenges also associated with web applications. So I'm going to discuss. So this is tools I involved in developing, and basically I developing about 11 different tools, except the first one I started with, it's a Java GUI tools. All the remaining 10 tools I developed is using web-based tools. I guess that's the reason I'm being asked to review a web technology. So some of tools such as Metabolomics has been used quite popular by a lot of people. And I'm going to discuss what's underlying technologies implemented these tools and how to develop fast and using user-friendly tools. So for web applications, what's advantages? No local installations and universal access and easy to maintain and updates. And we, as a developer, we have total control almost. But there's challenges, how to make it more user-friendly, give them interactions and visualization support, and also we need to give a high performance. Basically, nowadays we have a larger data set, and we have multiple users log on your server, use the resource at the same time. How to deal with this? So this is challenges not associated with standalone or command line tools because using install itself. So now this is an overview of the technologies, web technology we're going to review. There's a client side. Basically, this technology runs on the web browser, such as HTML, JavaScript, CSS, and WebGL. This is all client-side technologies. On the server side, there's a web framework for developing this overall tools. And there's computing engines that could be same as your web framework language or different. Also, sometimes we use database to support data analysis. Finally, it need to be run on an application server. So between client and server, there's communication. Another popular one is Ajax and JSON. So this is very efficient. Users submit their data and retrieve data from the server. And their browsing still continue, don't need to interrupt. So it's a very cool technology. And so the first I'm going to discuss server-side technology. The first I'm going to emphasize about web application framework, which is basically a plug-in and play tools. There's like Eclipse or NetBeans or different IDE, integrated development environment. You use these tools to help you fast development. A lot of complex stuff such as database operations and rendering complex component and perform complex layout. So if you're doing it from scratch, it takes a longer time. But if you use a framework and learn it, you just drag and drop and plug and play. It's so fast, and also you optimize for the performance. So learn a web application framework. Now there's so many of them. Some of the popular ones, Java-based, is JSF, Java Services, Ruby on Rails, and Django. So it's based on Python. So either one of these very good. So just stick with one and get familiar with them. My personal is Java-based because I'm familiar with Java language. So it's called Java Server Faces. It is MVC-based framework. It has very good library support, and such as prime faces and rich faces, and very comprehensive. Almost all the function you ask, they be there. So easily get professional look and feels. Disadvantage is if you really want to do some very fine control, it's difficult. So you can need to use client side. So this is one tool I developed recently, last year, and it's very doing complex statistical analysis, combining different data. And this is just screenshot. You can see the tables and views and multiple things you can click around, but it's easy to develop. So just use this library. Now I'm going to move to a computing engine. Basically, this is when doing business logic. For bioinformatics, business logic usually using some like Perl, Python, R, Java. So this is a very common one. So my personal favorite is R. And people talking about R is so slow, but there's ways to get around. You need to write your code efficient and use Java or C++ to get the most heavy part, or use a big server. So it's always how to communicate with R from the web application. And our previous speaker just mentioned about the Shiny, but if you really want a good, stable, high-performance server, it's need to use like a Java or the other web framework. So there's three ways to do it: system calls, and there's R Java. My personal favorite is R Serve Engine, which is based on TCP/IP communication and binary support, and you can do concurrent, basically as 13 users simultaneously access your server. Say it's like a 16 gig RAM, it should be fine working. If you really want more server using it, get another server or big server, it should be fine. So. And also a database for web application. Usually web application is not use database mainly for data analysis, but sometimes if you need to use it, my advice is try to think whether you really need it. Try to use a flat file. If you need to use database, use embedded database. If you use a full-blown like MySQL, it make maintenance and performance going to be a kind of more complex to maintain and difficult. But it's just my personal experience. It's the other one I want to mention about is non-SQL, which is much easier to use and high performance. You can really configure it to run very fast. It can be run in remote mode. Now I'm going to talk briefly about the client-side technologies. It's recently, just 2 or 3 years, it's HTML5, which is now standard and have a lot of cool elements. You can do a lot of cool stuff with that. And also CSS is for defining the styles. And JavaScript and jQuery also just so powerful, and you can do so many things with them. Ajax JSON, which I mentioned before, is talking from client browser to the server. We combine them, we can really deliver core services. And this is kind of examples, and this is kind of heat map. Basically, on the left side, you have your millions of your genes or metabolite peaks there, and you can drag and cross, and you select display on the center. And then you can do some gene set enrichment analysis or metabolite set enrichment analysis. So basically what you can really intuitively just running on a local desktop. It's so easy to, it's just using this several technology, JavaScript with HTML5, but really you can do a lot of intuitive stuff. And you can click, sort, and select and build. It's just, it can do it. And the second one, talking about high performance computing. And this is tools I'm just targeting for this. People complain about the cytoscript is very slow, which is standalone. I want to see if I can do it on web and it's running fast. So this is a tool we just published recently. You can have your millions of protein interactions in here. You can do a lot of zoom in and out, doing analysis on them, and it's in our techniques 100 times faster than Cytoscape, which is standalone. So you can do a lot of things with this. So now it's my own perspective on developing bioinformatics web applications. So this is several technology I mentioned before about this browser-based technologies at HTML5 canvas. You can really do a lot of interactions and image generations and the client service AJAX-JSON. And I haven't mentioned about this cloud service, but it's out there and it's mature. You can use it. And if you use database and think about this NoSQL database, and my vision is always from the user point of view. It's intuitive, interactive, and integrative, and intelligent. Basically, you want to save your computing resource. Don't do analysis all at again. Just put in a small step. Use ask, do it, and do it. Don't do it by default. Use confusion and cause a lot of stuff. Another concept is called visual analytics. Basically, we have this complex data, we generate plot, and the plot should be interactive. So you click the data point, it should drive you away to how this data point, what it looks like, bring user to their more delve deep. So and the other one is how to tackle with big data stuff. And my take is just keep in mind and borrowing strengths from this more cutting edge, this social media. This is most talented people working there. They always develop cool technology. Follow them and learn what they are doing so we can tackle ours. So quality assurance, visualization, and reproducible research, and use your own tools. So this is all the concepts we've been covered before by other programs. I'm not going to emphasize again. But just let the user participate, just make it a more informative messages to the output. And support, we're writing good documentations and maintain and good answering questions is all good. So summary is web application is going to be there and become more and more important. And visual analytics and cloud-based computing should be a next big thing. And we are developers, we should pay attention to this technology. And final acknowledgement is my PhD in University of Alberta with Dave Wishart, and my current one is Bob Hancock. They all support me, and thank you.
Thank you very much, Jeff, for that fantastic talk. Questions?
Hi, very nice talk. Enjoyed that. I was just wondering about designing software for a web application. I mean, how much do you have to make that decision right at the beginning? And how feasible is it, for instance, to take a piece of software that maybe has been developed in-house or without the web server in mind and convert it to a web server? I mean, I imagine that could be a challenge facing quite a lot of people who've developed the stuff in their groups.
Yeah, it's a very good question. I think the feasibility really depends on your experience, how you make a judgment. And sometimes probably 1 year ago it's not feasible, but now technology allow you to do it. So it's really case by case. But if you have particular things in your mind, we can discuss private. So it's really hard to say in general. Yeah.
So you think it needs a bit of expert knowledge to really make that decision to whether it's feasible? Yeah,
running on the web is how many people are going to use it, basically concurrency, basically how many people access at the same time, and resources, allocations, and what kind of interaction they want. So that's really a lot of thinking and depends on really user community.
Okay, thanks.
Yeah.
Thank you, Jeff. So we've got the next 20 minutes as general discussion. So I suppose if there are any questions, people can ask on an open forum or can contact the speakers separately.